let's say this was k value equals 2, this is k value equal to 5, and this is k value equal to 7. You need to draw the gradient right here. Which way would the gradient point? That way or that way? So let me continue this contour here like that. Okay. You got to draw the gradient at that point. Just to estimate the direction. Is it going that way or this way? Points in the direction of the increasing k values, so go that way. Now, what would it look like? It would have to be perpendicular at this point, so I'm just going to draw a tangent line. It would go what? Something like that. Don't worry about its length right now. Don't worry about its length. But that's which way the gradient. So I'm going to label this what? Del F? There's del F. It would be perpendicular and it goes in the direction of the increasing k values. Cool? So hey, is everyone comfortable with that? Like even on a test, if I said, hey, draw a gradient vector, just so you know how long to draw it, I may say like, draw a gradient vector that has a length of 1, which would be a unit vector. So I would say, draw a unit vector in the direction of the gradient vector. But make sure you draw it which way. It's perpendicular at the point of tangency, but it goes in the direction of the increasing k values. Everyone show that? All right. Yeah, I'll leave that up here. So now, I'm going to pull a problem out of this book that we'll do in a second. I want to talk more about this formula here. Can we prove this? The max. Let me do a little proof. What would be the maximum value of the directional derivative? Like an easier way to figure it out. That would be the maximum rate of change, the maximum what? Slope? That would see me swinging it around all different directions at that point. What would give me the maximum value of this directional derivative? So to prove this, everyone, I'm going to use an old theorem we had in this course. You know, this is a dot product. I'm going to use this crux move, this theorem right here. What's A dot B equal to? Do you remember? Magnitude of A, magnitude of B.
Cosine theta, right?
Cosine theta. So I'm going to use that in our proof. I'll just leave that off to the side. Well, let me start out with directional derivative. This is the formula for directional derivative. It's equal to, sounds like a curse word, del F dot what? Unit vector, right? Del F dot U. This is a vector and this is a vector, the dot product. Well, let me write it with that. So this is equal to the magnitude of del F, the magnitude of the unit vector, times the cosine of the angle theta, where theta is the angle between the two vectors, right? We're almost done figuring this out. We're just doing a proof. What would always give me the maximum value of the directional derivative? Let's talk about cosine. What's the highest cosine ever gets to?
0, 1.
1. Everyone agree? What's the maximum value of cosine of theta? 1. So we can turn this into a what? A 1. What's the magnitude of any unit vector?
1.
1. And here it is. And we're just going to make our own, bless you. Separate theorem. We'll leave this up all class. The maximum value of a directional derivative will always just turn into the magnitude of the gradient vector. Isn't that cool? So I'll just put it out over here, right here. Max value of directional derivative, any directional derivative, will equal the magnitude of the gradient vector, well, evaluated at the point, whatever point you're at. If it's at the point 1, 2, plug in a 1 and a 2 in there. Isn't that cool? We just proved it. Because this has to be a 1. This is always a 1. It turns into the magnitude of the gradient vector. So if you see those problems on the practice set, you know, what is the maximum, they might word it as the maximum rate of change, right? What's the maximum rate of change? If they write that, just get the gradient vector and take its magnitude and plug in the point. Then we'll do one of those. So on that note, everyone, I'm going to pick a problem from the textbook. This is in section 14.6. I'll tell you which problem I'm picking. This is number 33 on page 944. I mean, it's got a part A and a part B and a part C. Part A. Well, v of x, y, z. Suppose that over a certain region of space, the electric potential, V, is given by 5x squared minus 3xy plus xyz. This is called the electric potential over a certain region of space. Letter A. Find the rate of change. Of the potential. We're talking about V. They're going to give us a point, right? At the point 3, 4, 5, they're going to give us a direction, right? They always got to give you a point and a direction. In the direction of vector, V equals, they put it in standard basis form, so I'm going to do that as well. I plus j minus k. Hey, before we start, can we just put that in component form? What's that in component form?
1, 1, negative 1.
All right, so I'll write that. You prefer that? You might run it like that in your notes. What's interesting about this problem, and I like how it was worded, I didn't want this to throw you off ever on a test. They never said directional derivative, but they want you to find a directional derivative. It's rate of change. A directional derivative is just like a derivative you didn't count 1 in terms of being a derivative, it's rate of change. It also deals with steepness, we know that, with slope. So that's what they want you to find. What can happen though is you can get confused, because this is 14.6, the section we just covered was 14.5. Chain rule, those were also rate of change problems, remember? So just so if you want to put this in your notes, 14.5, all those problems, rate of change with respect to time. That's what was happening there. 14.6, rate of change in the direction of a vector. So that way you're never confused between what's chain rule problem and what's a directional derivative problem. See, a directional derivative problem, they got to give you a vector. They got to give you a direction. 14.5 chain rule, rate of change, that was just with respect to time. Right? Cool. All right. So I'm going to start it up. Here it is. I'm getting a directional derivative. Del f dot u. And then I'll plug in the points. So, I got to leave enough room for this del f. So here comes del f, because it looks, look at all that. What's the partial with respect to x? I think that's enough room. What's the partial with respect to y? That's enough room. And then what's the partial with respect to z? You're going to fill all these in. Oh, they're v's. So I'll write this as v sub x, v sub y, v sub z. These are the partial derivatives of v with respect to x, with respect to y, with respect to z. That's what the gradient is. That's what the gradient vector is. It's defined as a vector made up of all those partial derivatives of v. So let's do it with respect to x. See, we're always doing partial derivatives from here on out. What's that to respect to x? 10x. Anything else?
Minus 3y.
Minus 3y. Anything else? Plus y. So I barely had enough room. All right. What's vy? What's partial derivative with respect to y?
Negative 3.
Negative 3x plus xz. And with respect to z, just xy?
XY.
And when eventually we will plug in a point 3, 4, 5. So there it is. They call this the gradient, right? So since we just started this, I'm going to remind you that's called the gradient vector, all that. Now we do the dot product with the unit directional vector. So my biggest worry is when you accidentally do that on the test. So draw. This is called the unit directional vector. It must be what kind of vector? A unit vector with a length of 1.
1.
That's longer than 1. So I can divide out its
Correct.
magnitude. What's square root of 1 squared plus 1 squared plus negative 1 squared?
Root 3.
Got it? Yeah, everyone there is a unit vector in the direction of this vector. Cool. Is that what it goes at? Yep. They call it the unit directional vector. You know which way you point it. All right, let's do this. And what do we substitute for all these x, y's, and z's?
3, 4, 5.
3, 4, 5. All right. Go ahead and stick a 3 in here, and stick the 4 for the y. Stick the 5 for the z. What's that first number? What do you get? 90 minus 12 plus 20. What is that? $110 minus 12. Is that 98?
How do you doing 90?
Oh, 30. My bad. 30 minus 12 plus.
20, yeah.
Is that 38?
Yeah.
Cool. Thank you, everyone. What's negative 9 plus 15? 6. And what's 3 times 4? 12. And what are we dotting this with? 1 over root 3. 1 over root 3 and negative 1 over root 3. We'll dot all this. So what's 38 times this plus 6 times this plus 12 times that? I get 30, 42.
Minus 1. 41 root 3.
So 38 plus 6 would be 44 over root 3.
3. Minus
Well, 44 over root 3 minus
Minus
12
12.
over root 3 gives me 32 over root 3. You can leave it just like that. You do not have to rationalize the denominator. It didn't have units, so you can leave it like that. That's letter A. Is that okay with us? But there is a B and a C. Alright. So far so good? B and C will go quick too. B. In which direction does V change most rapidly at P? And that's something I wanted to add to this. Alright? Gradient vector is always perpendicular to the point of tangent. It points in the direction of increasing values. We said, well, then it also helps us to find the maximum value directional derivative. But I want one other thing. It will always, as they said here, where they ask, in which direction does V change most rapidly at P? This will be the direction that gives the maximum rate of change. It will always be in this direction as well. So let me say again. For this question, it'll be always in the direction of the gradient vector. I should go back to the proof. What happened when I got cosine of 0?
1.
I got 1. So I went cosine of 0, that means the angle between the two vectors would be 0 degrees. So the gradient vector would always be in the direction of the actual directional vector. Does that make sense?
Mm-hmm.
I don't have to pull it up again, but remember the applet we had? There were two vectors involved. You had the gradient vector and the directional vector. We're saying slam those together with an angle of 0 degrees, you always got that maximum rate of change. That's what happened. So this gradient vector will always provide the direction of the steepest slope or maximum rate of change. So this perpendicular point of tangent points in the direction of increasing k values. What else can I add? It gives the what? Direction, provides the direction of maximum rate of change. Okay, well, we can answer this question now. Let me read it again. 33b, in which direction does V change most rapidly at P? Letter B, I'm just going to put a vector down. What was the gradient vector? Which one of these two?
The one on the left side.
This
Right.
one. That's all I'm going to put. It didn't say you had to make it a unit vector or anything, so here's my answer. Because it gives a direction. That's it. So, again, let me be clear. The question here for letter B is, in which direction does V change most rapidly at P? In that direction. And we proved it before, but we're just saying because the cosine of 0 degrees would mean the angle between the directional vector and the gradient vector would be the same as the directional vector.
Is P like the point that was given in the first part? Like,
That's right.
okay.
And so they said, and they still wanted it at that point, and it was the same point they used earlier, this point. So very good, it was the same point they used in letter A. So this would give the maximum rate of change at that point. Cool. Now letter C, you knew this was coming. They go, what is the maximum rate of change? So this is the direction of max rate of change at that point. At the point 345, everything's at the point 345. Letter C, and when they go, what is the max rate of change?
So it'll take a magnitude, right?
Yes, we're going to get the magnitude of the gradient vector at that point. It'll be a scalar value. So this answer was a vector, but here we're going to get the magnitude of that. So let's see, what do you get? I'm going to need a calculator on this one. 8 squared plus 6 squared plus 12 squared. Notice I didn't make it a unit vector or anything. This would give me the highest rate of change. Pretty cool. I'm going to square to some big number. We'll make sure 2 people get it. What's the square root of 38 squared plus 6 squared plus 12 squared?
40.298.
40
.298.
after the square root?
Yeah, or wait, under the square, oh, I added everything.
Oh, that's right. Feel free to hit it. I like this one too. Source?